In this session, we're going to see about the conjugate pairs theorem and forming polynomials, and not in that order. First, we're going to recall how we would solve an equation like x squared minus 4x minus 5 is equal to 0. We would factor the expression on the left-hand side into x minus 5 times x plus 1, set that equal to 0, those factors equal 0, give us the solutions x equals 5 or negative 1. We are going to do this process in reverse to form a polynomial. And our first example is to form a polynomial with zeros 2 and 3. If a polynomial has zeros 2 and 3, then the process we just saw should help you see that we would have factors for this polynomial of x minus 2 and x minus 3. When we multiply this out, we end up with x squared minus 5x plus 6 as our polynomial. Now, if we were asked to form a polynomial equation, then we would say x squared minus 5x plus 6 is equal to 0. If, on the other hand, we were asked to form a polynomial function, then we might say f of x is equal to x squared minus 5x plus 6. So the way we give our answer is going to be dependent on how we were asked to do so. Next, form a polynomial with zeros negative 2 and 1, with 1 a zero of multiplicity 2. Notice we weren't asked for a polynomial equation or a polynomial function, so we get away with just writing down a polynomial. The zeros are negative 2 and 1. Now this is going to be, it's going to take a little getting used to, but our factors are going to be x minus negative 2 and x minus 1. Hold on, I'm not done with that yet. Because, let's back up, when we were solving that original quadratic, we had factors of x minus 5 and x plus 1, and remember when you solve those, because you're setting them equal to 0, you end up adding or subtracting appropriately. We change the sign on the answer, right? So when we put a 0 into a polynomial, the factor of a polynomial that is, then it's appropriate to use subtraction. And the x minus 1 probably makes a lot of sense. Now that we've thought about it a little bit, the x minus negative 2 probably makes some sense. We're going to cut to the chase from now on when we're dealing with real zeros. X equals negative 2 gives us a factor of x plus 2. And then that's going to be multiplied by x minus 1. But wait a minute. This was a zero of multiplicity 2, 1 was. So we're actually going to have the polynomial x plus 2 times x minus 1, the quantity squared. Using the order of operations, we're going to apply exponents before multiplication. So we have x plus 2 times the quantity of x squared minus 2x plus 1. And when we multiply this beast out, you can check me on this, we end up with x cubed minus 3x plus 2. So that polynomial has the desired zeros and multiplicities. Let's write something down in general. If c is a zero of a polynomial, then x minus c is a factor of the polynomial. In other words, when I put a number into a set of parentheses, I should have an opposite sign as in that factor. Now we get to the conjugate pairs theorem. It basically says that complex zeros come in conjugate pairs. If a plus bi is a zero of a polynomial, then a minus bi is also a zero. There's a proof for this. I'm not going to do it right now. It's in textbooks. I could do it in class. If you really want to, just ask. Find a polynomial equation with real coefficients that has a root of 4 plus I. That real coefficients business is the tip-off that we're going to multiply stuff out. Now let's look at the kind of two things we have going on here. One of them is the conjugate pairs theorem, or the conjugate zeros theorem, as I've heard it before. If 4 plus I is a 0, then 4 minus I is a 0. You notice we have a 0 here, we have a root here. Roots typically correspond to equations. Zeros typically correspond to polynomials in particular, or functions in general. We could split hairs. I don't think it's really necessary. Just know sometimes you're going to see 0, sometimes you're going to see root. If ever you see x-intercept, that means it's a graph. Anyway, that's one thing that we have going on. The other thing that we have going on is what we just saw. That is, if c is a 0 of a polynomial, then x minus c is a factor. So, if 4 plus I is a 0, then x minus 4 plus I is a factor. And because 4 plus I is in parentheses, we have square brackets around that. Likewise, if 4 minus I is a 0, then x minus 4 minus I is a factor. We were told to find a polynomial equation, therefore I'm going to set this equal to 0, and now it is an equation. If we distribute the negative inside the square brackets, then we end up with factors of x minus 4 minus I times x minus 4 plus I, and that equals 0. And at this point, there are a couple of different ways we could go about this. We could try to like foil it, like, you know, x times x, and then x times 4, and then x times I. I think that's an excellent way to lose things. We could, if you want to, stack them on top of each other. X minus 4 minus I on top, and then x minus 4 plus I on bottom, and multiply them like you would two 3-digit numbers. That's actually, I show you that at the very, very end of this video if you want to see that. It's a different example, but that's there if you want it. I'm not going to do that this time either. What I'm after is a more elegant approach. I'm going to color code this. X minus 4 appears in both factors. I'm going to put a blue box around x minus 4. And then I appears in both factors. I know, sounds like poor grammar. So I'm going to put a red box around the i's. And now we're going to go abstract over here. We're going to see what would happen if we, generally speaking, multiply blue box minus red box and blue box plus red box. If we like foiled this out, I would end up with blue box squared and then minus blue box red box plus blue box, the middle terms would annihilate each other, minus red box squared. In other words, this is what happens when you multiply conjugates. You end up with a difference of squares. You remember that? So what I'm doing is I'm going to see this as, hey, let's multiply this out so we end up with a difference of squares. And in this case, we're going to have blue box squared minus red box squared. Of course, equals 0 because it's an equation. But what's in the blue box? What's in the blue box is the quantity of x minus 4. What's in the red box is I. If you do this with just the shapes on your paper, you'll kind of hopefully see how it plays out. And then it should make sense to you. X minus 4, the quantity squared, is x squared minus 8x plus 16. Then we have a minus I squared. Well, I squared is equal to negative 1. So what we actually have is x squared minus 8x plus 16 minus negative 1 is equal to 0. And then simplifying gives us that x squared minus 8x plus 17 is equal to 0. And this is the desired polynomial equation. But not this one. Here we're asked to form a cubic function with x-intercepts 1, 0, negative 1/2, 0, and 1/4, 0, and a y-intercept of 0, 2. This is almost the same thing we've been asked to do with a slight twist. Well, two twists. One of them, we're given intercepts instead of zeros. And number two, we're told basically what our constant term needs to be. That's our y-intercept number. I want to talk about having 1/4 as an x-intercept, 1/4 0 as an x-intercept. This could lead us to having a factor of x minus 1/4. But I don't like that. I don't like that one little bit. If you kind of think about how this is going to play out, we'd end up with x plus 1/2, x minus 1/4. It would be a fractional mess. Let's think of another way we might end up with a 0 or x-intercept of 1/4. A few seconds thought might convince you that 4x minus 1 as a factor would give me a 0 of 1/4. And if we're not sure how we would come up with that on our own, let's suppose that x is equal to 1/4. Let's say that's the solution to an equation that we've just solved. Let's solve this thing in reverse. See where it would have come from. If x equals 1/4, then when I clear the fraction, I will end up with 4x is equal to 1. If I then subtract 1, then I get that 4x minus 1 is equal to 0. And so this indicates to me the factor that I could have had to give me x equals 1/4 as a root, or as a 0. And when roots or zeros are real, they're tied to x-intercepts. Therefore, the cubic function that we're looking for, we're going to start out by writing that f of x is equal to, and I'm doing that because it said function, x minus 1 times 2x plus 1 times 4x minus 1. Now, you can double check yourself that these factors would have the desired zeros and therefore x-intercepts. And this process that we just went through kind of unsolving is what you could do to write these factors down on your own. Now our task is to multiply this out. And I'm generally pretty good at multiplying two things at a time. And so I wrote down the x minus 1 as a factor, and I multiplied 2x plus 1 times 4x minus 1. And so we now have f of x equals x minus 1 times the quantity of 8x squared plus 2x minus 1. Multiplying further is going to give us f of x is equal to 8x cubed minus 6x squared minus 3x plus 1. Double check me on that. And here I have the wrong y-intercept. Remember, the y-intercept is obtained by finding f of 0. And in this case, if we were to compute f of 0, we would end up with 1. It's supposed to be 2. Here's the thing. I don't get to add 1 to the thing and fix it that way. That would alter the function in ways that we couldn't anticipate right now. It's actually the case that since I want f of 0 to equal 2, I need to multiply the entire expression that defines f by 2. In other words, to fix a constant, we have to multiply. That being the case, we're going to get f of x is equal to 16x cubed minus 12x squared minus 6x plus 2. This is our cubic function with the desired intercepts. Finally, we are asked to find a polynomial function with integer coefficients and zeros 1 plus 2i and 2 with 2 a 0 of multiplicity 2. Why don't you pause the video and write down the factors that this indicates. So for starters, we have, I used p, you could have used f or g or whatever you wanted. P of x is equal to x minus the quantity of 1 plus 2i, and then I have x minus 2 the quantity squared, but enter the conjugate pairs theorem. If 1 plus 2i is a 0, then 1 minus 2i is a 0. So we ultimately need to have x minus the quantity of 1 plus 2i, x minus the quantity of 1 minus 2i, and then x minus 2, the quantity squared, that's our 0 of multiplicity 2. We were told this polynomial function needs to have integer coefficients, and that's my tip-off to the fact that I need to multiply it out. And first I'm going to simplify inside of the brackets. I have p of x is equal to, distributing the negative gives me x minus 1 minus 2i, and then in the second brackets, x minus 1 plus 2i, and x minus 2, the quantity squared, I'm actually going to write that as x squared minus 4x plus 4. I go ahead and multiply that out. Now, as far as these, the first pair of factors, looks like I have x minus 1 repeated at the beginning of each set of parentheses, and then 2i repeated at the end, with opposite signs in the middle. Envisioning this as a difference of squares scenario having been factored, we're going to unfactor, that is multiply. And so I'm going to write this down as p of x is equal to, and I'm going to write down something that looks like basically blue x minus 1 squared minus red 2i squared. I suppose technically that would merit brackets around those. And let's not forget the x squared minus 4x plus 4 that we had. I'm not going to intermingle these until I've dealt with the first pair of factors that we've been looking at. Now, p of x is equal to, the x minus 1 quantity squared is going to be x squared minus 2x plus 1. And then we have a minus. That 2i quantity squared is going to be 4i squared. So x squared minus 2x plus 1 minus 4i squared times, again, x squared minus 4x plus 4. Now, remember that I squared is negative 1. So that's going to turn this into a plus 4 inside that set of parentheses. P of x now equals x squared minus 2x plus 5. That quantity times the quantity of x squared minus 4x plus 4. After multiplying these out, I get p of x is equal to x to the 4th minus 6x cubed plus 17x squared minus 28x plus 20. This is the polynomial function that we were after. If you're cool with how to multiply all that, you can be done. Stop the video. If not, stick around. One way you could do it would be arches, right? X squared times x squared times negative 4x. That's a good way to lose stuff. What I would recommend, if you would like to see it, bookkeeping. So what I've done is I've stacked our factors as though we're multiplying three two-digit numbers, right? X squared minus 2x plus 5 is the top one. X squared minus 4x plus 4 is the bottom one. And just like you would multiply two three-digit numbers, I'm going to start with 4 times 5, which is a positive 20. 4 times negative 2x is a negative 8x. And 4 times x squared is 4x squared. Now I've exhausted 4, so we're going to move on to the next term in that bottom polynomial, negative 4x. Negative 4x times 5 is negative 20x, and I'm stacking these in such a way that like terms are grouped, essentially. Negative 4x times negative 2x is a positive 8x squared, and negative 4x times x squared is negative 4x cubed. Now I've exhausted negative 4x. On to the other term in the bottom polynomial, x squared. X squared times 5 is a positive 5x squared. Again, still stacking like with like. X squared times negative 2x is negative 2x cubed. And finally, x squared times x squared is x to the 4th. Now, when I collect my like terms, I have x to the 4th minus 6x cubed plus 17x squared minus 28x plus 20 as we wrote above.